All right, we're officially recording now.
Okay, great. Welcome to, well, finally, we're going to see something that's like applications of all that Clifford algebra stuff. So I actually am going to talk about real physics today, as real as it gets. And I'm going to revisit the original work of Dirac and his discovery of these things that he called spinors, and to see how all of the story about Clifford algebras and spin groups actually fits into this sort of classical picture that he drew. So how does this fit into like a relatively more modern context? Even though it's not really that much more modern, it's like developed around the exact same time. So it's really frustrating when you go and read physics books that just do it the exact same way that Dirac did, which I guess makes sense. But it makes a lot more sense to see everything from the frame of like Clifford algebra representations. But it's a whole package that you have to develop, and we're lucky that we have already developed that. So that's going to be the goal for the first little bit of the talk today. And then after that, I'm going to talk about how this goes to families of Minkowski spaces and talk about bundles with pseudo-Riemannian metric in order to see what does it mean to be a spinor on some sort of space-time manifold instead of just some sort of trivial type of thing. So that's the plan. Hopefully I can get corrections about relativistic field theory when I say things that are wrong, but I'm going to try. Okay, so like I said, we're going to start with relativistic field theory. Actually, nothing that I'm about to say is really quantum. This is all relativistic. For sources, I looked in Tong. He has course notes about quantum field theory. That's where I got most of the actual material from, and his conventions I like better. Mann actually presents it in a way that makes you feel like, oh, this is how maybe Dirac kind of stumbled into this idea. This is sort of like a good motivation for where the ideas come from, and this was better at actually providing some extensive development of these ideas. So to start out, we're just going to think about plane waves, the things that solve the wave equation, but also the solutions to the Schrodinger equation. Take this form, I guess. So you just have some propagating vector and some energy that kind of refers to your frequency, and you take a complex exponential. So this is some sort of oscillating thing that travels through space with momentum p. And the what's interesting is that the energy of this plane wave is related to the magnitude of the momentum divided by the mass. So it's actually just related to the velocity, how fast is it going? For relativistic field theory, this isn't really a relativistic relationship. I'm not sure exactly what that means on the nose, but in the relativistic context, there's a slightly different relationship between energy and momentum. So I'm going to take Tong's particle physics metric, which I think is opposite from what relativity people like to think about. So the time is going to be the positive coordinate, and the spatial coordinates are going to be minus. That's just what I had to do to follow the notes, is accept their conventions. So in relativity, we have a momentum 4 vector for some massive particle, and the time coordinate of the 4 vector is always given by whatever value that is equal to the energy. And then you have your momentum, your actual direction times the mass. But you define the mass of your momentum 4 vector, the rest mass, to be the contraction of your momentum with itself using the metric. So what I mean by a symbol like this is, well, you have your metric. Yeah, I mean, you use your metric to turn your vector into a covector, and then you evaluate the covector on the vector. This is what happens when you use these funny index notation, but that's actually what it means. Just using the metric to turn a vector into a covector. And the quantity that you get is called the mass squared. And if you actually use calculation to see what you should get on this side, you get the energy squared minus the magnitude of, or the magnitude squared rather, of the actual momentum vector. So this is the relationship. This is the relativistic relationship between the energy and the momentum. So what we want to do is then take this expression, and since t is actually the first x coordinate in a relativistic context, we can rewrite this expression as a contraction of the momentum vector with the position vector, like this. So this is formula for a relativistic plane wave. Okay, and so if we want to figure out what should be the relativistic wave equation, we can just start taking derivatives of this and see what equation this object satisfies. So I'll save you some of the details, well, all of the details, and say if you take nabla twice, the divergence twice, then you get this particular differential equation. And if you recognize this as the x0 coordinate, and these are the x1 through x3 coordinates being differentiated, this is actually just a contraction of this sort of called a partial derivative vector, right? It's del by del x0 down to del by del x3. So you take this vector, you contract it with yourself, you get the relativistic version of the Laplacian, which I guess is called the D'Alembertian. This is the D'Alembertian, right? They call it squared. This is what you do to take like divergences in a relativistic context. And so this equation that you get by doing all of this relativistic wave equation gets called the Klein-Gordon equation by the people who discovered it, even though according to Tong, Dirac came up with it. Sorry, somebody else came up with it first. I think it was Schrodinger. And now I forget the name. Never mind. But that's the relativistic wave equation. So one drawback that people didn't really like when they discovered this was that instead of taking a minus in your thing to get, some periodic behavior, you can take a plus there and get the negative periodic behavior rotating the other way. This corresponds to something, if you go and compute what the energy is supposed to be, you end up getting actually a negative energy for this solution to the Klein-Gordon equation. So people didn't like this because it doesn't really make sense to have negative energy in this relativistic context. And so Dirac decided to go and find a first order differential equation, thinking that, okay, the problem here is that we just have a second order dE. Of course, you're going to have two independent solutions. So what if you just go down to a first order dE whose solutions also satisfy Klein-Gordon, and then maybe solutions to that are going to carve out only the positive or only the negative, or who knows? Okay. So here's what you can try. You try something like A due just some vector of coordinates. I'm going to try an equation that has this form, where A mu scalars, or just numbers, rather, I guess. Because we're talking about physics and relativity, so scalar means something really specific. So let's just take these are numbers. Then we would end up getting, for our plane wave solution, I A mu E mu plus M is 0, which is wrong. So it's not just that there's an I popping out here, but we could just choose to put an I there instead. It's more that this is just not the right relationship. It doesn't recover the relationship that P squared should be equal to M. So which is which? Wrong. So the idea, just like the revolutionary idea, is what if these aren't numbers? What if A mu for matrices and psi is actually a vector of components. It's a multi-component. What do you call it? Field, I guess they call these fields. Whatever that means. So what if instead of just taking like a scalar field and numbers in this linear combination, what if these are actually matrices? And these are like a vector of field. So that's a really audacious idea. So yeah, let's see here. Yeah, so here's the question then. Can we find four? So you're going to have to take four of them because the sum is going over four components here. Can we find four n by n matrices so that Right, so we're taking, we're calling gamma 0 up to gamma 3. We want to satisfy the following. So gamma mu, this is going from 0 to 3, and it's a matrix. So we have indices A, B. And then we're acting, whatever this is, we're just summing over the differential partial derivatives. Then we have m times the identity matrix. So this times psi b, if you take this thing and you're summing over all these, this should be 0. Or to write this a little more human readable, you can suppress the matrix indices. And we just write it as I gamma mu, L mu minus m, psi equals 0. You just have to remember that this is actually a multi-component field. This is actually a matrix. We're summing over a bunch of stuff. Okay, so this is the form of the equation that we want to try, but we still have to determine n. Right, so what matrices are actually going to work? We don't actually have any constraints on these matrices yet. And we also want them to, so if we impose, I'll just do it like this. If we impose the condition that p squared equals m squared, or this p squared, I mean the contraction of p with itself, then like dot, we arrive at these relations. You get that, yeah. That if you take the anti-commutator, which I'll just append, already like this. You take two of them and multiply them in one way, and then add that multiplication in the other way, which is called an anti-commutator. It looks like a commutator, except instead of measuring the failure to commute, it measures the failure to anti-commute. The anti-commutator is actually given by 2 times the metric times the identity matrix. So what does this mean? This means that on this side, there's no like contraction or anything happening. This is just a number. This is like a scalar number times the identity matrix. So when you take these, whatever these relations matrices are here, you have to grind out a lot of algebra and figure out how it's supposed to happen. But the outcome at the end of the day, I don't want to spend a million years going through the derivation, is that the anti-commutator of the whatever matrices that you have to use in order to impose this condition has to be given by 2 times whatever these numbers are times the identity matrix. But these numbers are all either plus or minus 1, right? So this is exactly the condition for generating a Clifford algebra. So therefore, this set of gammas generates an algebra isomorphic to Clifford algebra, where so our convention is going to be a little different. So our G, we put the time coordinate first in the 3 space dimensions. The 3 space dimensions are minus. So the spatial gammas, these are the things whose squares are negative. So in our Clifford algebra, we always put the things whose squares are negative first. This is just the convention you started with, and I'm going to keep to that. So the isomorphism, the algebra that these things generate is isomorphic to CL3, 1. And in particular, you have to write them in the correct order. You have to go gamma 1, gamma 2, gamma 3, and then gamma 0 is the one that squares to 1. Okay, so Clifford algebra has shown up. So already we can start to make observations, like what is this algebra? So if you remember, RS, R is S. In the 0 column, we had R, C, H, H plus H, dot, 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 0, 1, 2, 3. And we also had an isomorphism you tensor the CL algebra 1, 1. Says the effect of adding 1 to both of your parameters. And CL11 is a copy of R2. So the second column is just going to be a copy of the first column, shifted up 1, and you're just tensoring 2 by 2 matrices. So complex tensor 2 by 2 matrices, 2 by 2 complex numbers. This is going to be 2 by 2 quaternionic, dot, dot, dot. So this is the thing that we're looking at. The CL31, we just found using our classification of Clifford algebras that this is actually 2 by 2 quaternionic matrices. But that's not quite the right thing, because in the Dirac equation, we have this scalar I flying around. So in order to do all of these manipulations, this scalar I has to be treated as something that commutes with all of these matrices. So 2 by 2 quaternionic, there is something called I. We can consider like the matrix I, right? You can imagine that this is I, but it doesn't actually commute with it. This is not a central element in this algebra. But in order to do all of these calculations, you need I to be a central element of everything that you're working with. So we're actually working with the complexified Clifford algebra. So order, you have scalar I actually working in complexification CL31 tensor C. This was by definition, so I didn't talk a lot about complex Clifford algebras. This is by definition CL31 with a Blackbird bolt. I did mention in the first talk that every quadratic form over the complex numbers is equivalent to the diagonal form. So the stuff about indefinite signatures and the real numbers, as soon as you take the complex numbers, that all goes away. So it's actually only dependent on the sum of these two indices. And there's a similar classification for complex Clifford algebras, which I might as well just write down. So CLN for N. Really good. So 0, 1, 2, 3, 4. Goes like this. So in order to derive all of this, it's exactly the same as, well, analogous to what we did. The real case, which is probably way bigger. And C4, 2, 3, 4. So in this case, it's actually this algebra that you tensor with in order to get the two periods. But in any case, this CL4 complexified Clifford algebra is actually 4 by 4 complex matrices. So in order to find an irreducible module over these gammas in which to do all of this Dirac stuff, our theory of Clifford algebras already informs us that we should be looking for 4 by 4 complex matrices. Okay. So that's where we're at. We're still trying to actually properly define this equation, but we have a hint about what these gammas should be and where they should be acting. Okay, and so we're going to actually pick now a representation. There are many representations that you can take, and this is probably one of the more popular ones. Start by taking the Pauli spin matrices. These generate some in the algebra, and I always forget which one. And then we take the so-called chiral basis. And I'm going to write this one board over. So I don't like squeezing stuff down.
Also 0 or
Yeah, sure. I'll leave some notation as an exercise. Okay, yeah. These will be consistent there. Sure. So define the chiral or Weyl basis. So gamma 0, we're going to take to be 4 by 4 block matrix that looks like this. Gamma 1, and for the rest of them, we're just going to have a consistent form with sigma I there, and then a minus sigma I down here. So these as elements in C4. So this is the representation of Clifford algebra that we're going to pick. This particular action on 4 by 4 or on a 4-dimensional complex vector space. Okay. Are there any questions while I try to gather my thoughts about what to do next?
Just write the indices a little bit bigger. These ones are okay, but like the last one. At the last one, and just the indices write them bigger. That's okay.
Yeah, I will write these little things bigger. Yeah, okay. So this is one representation that we pick. So now that we can actually like, yeah, so we have a definition for essentially this part of the Dirac equation, everything except for the psi. We still don't really know what psi should be, other than I guess, right? Psi kind of lives in 4 by 4 complex vector space, but we don't really know like what it is. It's just a vector of 4 things. And since we're doing physics, what we really like to think about is how do things transform under Lorentz transformation. And so far, we don't really have a Lorentz transformation action on these things. We just have this weird Clifford bundle or Clifford algebra action. So now, don't really have a way of motivating what I'm about to say. It's kind of a miracle. At least from my perspective, it's a miracle. A miracle. Or maybe I make some definitions, sorry. So let's just, for once and all, say that the Lorentz group, probably going to get some people mad at me, is equal to the orthogonal group of this pseudo metric, 013. This is where we're going to call the Lorentz group. And we're going to say that the orthochronos orientation preserving Lorentz group is SO upward arrow 3, 1. So this is everything where, on one hand, like it preserves any orientation on the 4-dimensional real vector space, but also you have this time direction, and you're required to keep that time direction pointed still in that time direction. So this is actually one of the 2 components of SO31. And it's the component that contains the identity element. Okay, so this is the Lorentz group that we want to think about. This is the identity component. And we have Lie algebra that we're going to say is SO31. I write it as SO31 because the Lie algebra only depends on the identity component. So we have a Lie algebra generated. I'm going to be really rough now and not write down what they actually are. So it's generated by rotations and boosts, things called boosts, which you can think about as being rotations, rotations into the time direction. There's actually like a uniform description of these generators for this Clifford algebra, and I'm going to write them as M, mu, mu. And so now a bunch of Lie theory entails so that we can write our SO orthochronos blah-de-blahs as the set of all exponential values of some coefficients, which I'll write the indices bigger, times these generating elements of the Lie algebra. Okay, so this is kind of confusing. The point I'm trying to make is that the Lie algebra for this Lorentz group It's generated by these matrices that are called big curly M. Some of these correspond to elementary rotations in between like the x1, x2 rotation, x2, x3, x3, x1. Some of them correspond to rotating either of those three spatial directions into the time component. So there's these six linearly independent generators. So the Lie algebra, this set of all possible linear combinations, where omega ranges over all possible coefficients, this captures the surjective image as the connected component of the identity with the Lorentz group. So we're expressing everything in the Lorentz group in this way. Okay. So this is a little bit of context for Lie theory. So miracle is that if you define S mu to be a quarter of the actual commutator of gamma mu and gamma mu. So these are defined in terms of their anti-commutator. So what if you take the commutator instead? And this has actually a nice form that I don't have to write down. So if we define them like this, then these satisfy the Lie. I'll say it like this. Yeah, this is a better way to say it. So these elements generate a Lie algebra. Let's say G, isomorphic to our SO, what? 3, 1. Okay, so that the Lie algebra of, what am I saying? Yeah. Sure. Yeah. So we've chosen these Clifford algebra elements, and we've concocted some matrices out of them. Just kind of magically, these turn out to be an algebra isomorphic to this group. And so living inside of our Clifford algebra is a Lie algebra that's isomorphic to the Lie algebra of our Lorentz group. And so we can try to use this in order to construct a representation of the Lorentz group on whatever it is this Clifford algebra is acting on. So let's see if I can try to put symbols to this. Okay, so we have SO 3, 1 embeds into our complex Clifford algebra CL4. This is our gamma matrices. So this is by sending M mu to S mu. So this is a homomorphism. This is a Lie algebra embedded. This is a Lie algebra embedded. This is the Lie algebra embedded. So what we want to do now is maybe we can get an actual representation of the Lie group into whatever is the exponential image of this. So this is the exponential map covering this. This is something I didn't mention at all, but this is true. Every Clifford algebra, its exponential map lands on the Lie group of multiplicative what am I trying to say? The multiplicative group of invertible elements of the Clifford algebra is a Lie group, and its Lie algebra is the Clifford algebra itself. So that's a very important. So we have this exponential thing, and we want to know, is there a way? So this is the group that's acting on our spinors. This is the Lie algebra that's acting on our spinors. We have this Lie algebra representation of the Lie algebra of our Lorentz group, and we want to say, okay, well, is there an actual genuine representation of the Lorentz group on these spinors through the group of units in the Clifford algebra? And the answer is no. The answer turns out to be no. And why is that? So the answer comes from actually plugging in boosts and rotations to see what what actually manifests in this group over here on the right. Okay, so rotations. So these correspond to Sij, a rotation, and the Ij gets represented by the following matrix. Negative I over 2, the Leda symbol, sigma k, sigma k, meaning that if you take the appropriate coefficients, right, so for rotation, let's say like this, for rotation around x3 axis by 2 pi, well, just 2 by this, 2 by this. So, hard to motivate and then explain at the same time. Okay, so this is what like a typical rotation matrix would look like. So if you take, where's the formula that I wanted to write down? It's here. Okay, so how do I symbolically do this? Yeah, I didn't manage to symbolically translate their things into my stuff, so I'm just gonna leave this up. Okay, let's just say it like this. The rotation around x3 axis by 2 pi is represented by, so this is going to be one of these exponentials, S mu mu, where these are carefully chosen so that the only non-zero things correspond to the rotation around the x3 axis. So this is going to become the following. Yeah, that's the right thing. This is going to become the following action: e to the plus pi pi sigma 3, e to the plus pi pi sigma 3. And so this is, remember, this is living in the complex Clifford algebra, the multiplicative units that this was. So this is actually just GL for C. Okay, so this is what the representation says rotation around x3 axis by 2 pi is supposed to do. You take the element in the Lie algebra over the Lorentz group. So we take the M matrices that give us rotation by 2 pi, send the M's to the S, and then the details that I didn't actually include, when we apply the exponential to the resulting image of the Lie algebra representation, we get this inside of this Lie group. And so where am I going with this now? Right. So if you actually go through the calculation for what exactly this sigma 3 is, this thing ends up being the operator negative identity. So yeah, I wish I had said this better. But along this Lie algebra representation, the Lie algebra element that maps down to rotation by 2 pi, its representative maps down to taking -1. So it's supposed to be the identity, but it's not the identity, right? So you have your matrix here rotating by 2 pi, maps to identity here because the Lorentz group rotates 2 pi back to the identity. But then if we take the representation over here and map it down, it's not the identity anymore. So something that goes to the identity here, but not the identity here, there cannot be a map here. So we call this map rho and this rho bar. There does not exist a Lie group homomorphism from here to here. There is no Lie group homomorphism such that the derivative of this Lie group homomorphism is equal to this Lie algebra homomorphism. There are none. So this thing that we've constructed isn't actually a representation of the Lorentz group, even though physicists kind of love to say that it is. And then you find some parenthetical statement that's like, this is actually a representation of the double cover of the Lorentz group. Just been lying to you the entire time.
There does not exist, right?
Yeah, no, not sure. Not, yeah, I was using the exclamation mark as a not in the entirely incorrect way. So thank you, Dan.
Uh,
Yes, yes.
and I was wondering, so because these are Lie groups, right? How can and they're manifolds, right? Uh, how, for instance, SO2 is a sphere, a one-dimensional sphere, right?
Yeah, SO2 is a circle. Yeah.
Yeah. And so in that sense, how can I visualize geometrically what is SO31?
Oh man, that's hard. Yeah. So SO31 is weird. It's not a compact group anymore.
That makes sense.
It is not simply connected like the fundamental group in Z1, 2. Um, I forget. Like this is one of these things I should have spent time reading about, but I had so many other things to spend time reading about. Yeah, I don't know how to really explain how to visualize SO31. Basil probably has a good explanation, but I've never been able to see it.
I have a guess. So for SO3, it's a double cover of S3,
Other way around. It's double covered by S.
double covered by S3, right?
Yeah.
So what I kind of imagine is that you're it's maybe going to be like topologically speaking multiply this by R to get an infinite cylinder or a hyperboloid. You take SO3 and you do that
Maybe. So you're
and you
thinking
get
like maybe something like this would happen, I guess, 3 cross R,
yeah,
and there's just some kind of weird double
double
cover map.
exactly.
So,
Exactly, yeah.
yeah, I don't know. Maybe.
But I don't know if it's true or not. That's just my hunch.
Yeah, I don't think so. I think don't remember why not. Yeah, no.
Okay.
Yeah. This is one of the things that is on my list to understand better.
Yeah.
But I didn't have the time.
Yeah, because like in terms of the homotopy groups, I think it actually checks out. That it is the homotopy ones of the SO3 one, but that doesn't mean they're homeomorphic, obviously. It just means that they're somewhat similar.
Mhm.
Yeah.
Yeah. Yeah, I'm not sure that this would be true.
Yeah. Okay.
I'm feeling that like the spin group, because like what you're asking is that if this is equal to spin 31, which also isn't compact, but I don't think that spin 31 is actually just like a product, but I might be wrong.
Okay. It might be a semi-product.
Maybe.
Maybe.
Yeah, maybe.
Okay. Thank
But
you.
like I'm not sure. Yeah, that's the right decomposition or not.
Okay.
There's a lot of accidental isomorphisms in low dimension that just don't generalize to higher at all. But I don't know enough to say if this is one of those.
Yeah. Like SO2 being isomorphic to S1 is an accidental one.
Yeah, pretty much.
Yeah.
Yeah. Like this is
For high dimensions, it's not the case.
us in space. Yeah.
Nice.
For example. Okay. Right. So this is why, because of the rotations, we can actually sit down and calculate, yeah, the value of these matrices under this representation. You find that this it's impossible to satisfy the commutativity of this square. But like dot, it's not something that's super straightforward to explain. So this the algebra homomorphism does send double cover. So instead of going all the way down to SO31, we have a different exponential map down to spin. So we get spin 31. This is actually isomorphic to SL2C. So the representation rho bar that is descending from our B algebra homomorphism to the Clifford algebra. That. And so in fact, yeah, what else? So in fact, because these S's are actually commutators of our Lie algebra generators, you actually land inside of the even elements. And so in fact, the spin group is really just sort of embedding as itself with this Clifford algebra. So our representation that we found for the double cover of SO31, that sort of exists independently of constructing things, spin groups inside of SL4. We just found that the double cover of this Lorentz group, we do get a representation in the CL4, and the representation is actually identifying this group as a multiplicative subgroup of the even elements here. Okay, so, oh, and yeah, and like I said, this is actually GL for C. There's an interesting note is that this can't be this area. And the too long didn't read explanation is because G mu mu is indefinite. What ends up happening is that if you want all of these S's to be anti-Hermitian, then since it's defined as a commutator of these gammas, that these gammas either, you have to be able to choose them so that they're either all Hermitian or all anti-Hermitian. And because of the indefiniteness of our quadratic form, it turns out that you can't make that consistent choice. So this representation actually can't be a unitary representation. That's a little bit of flavor. Now we can actually say, for all this time, way too much time, we can write down what is the Dirac equation and what are the objects that are involved. Okay. So the equation is the same thing I wrote down before, it's just that our symbol means something. I don't know if that's a typo. Forget if that's it's a plus M. Might be plus M. Oh. Okay, where these guys generate then something isomorphic to the Clifford algebra CL31. We have to complexify it in order to move this I around freely. And psi is element in C4. And being acted on by the following representation of the double cover of the Lorentz group, SL2C, which it turns out is isomorphic to then 3, 1, and this is being embedded into complexified Clifford algebra. And I guess I just writing down the same thing I wrote there. Because I'm not very organized today. Yeah, so this is the Dirac equation. And these bullet points are, they're explaining what are these objects, where are they living, and how are they acting. So we have an actual space for these spinners, these size, they live in four-dimensional complex space. And we have this Clifford algebra acting, and using this Lie algebra magic, the action of the Clifford algebra actually becomes a genuine representation of this big group. This is why, in retrospect, they're called spinners. This is why we named this group spin. This is why. Okay. So I'm just going to wrap up our discussion of the Dirac equation now that we've defined all these things. So, more work, more calculation. So, calculation that leads to that expression over there for the rotation action. Basically, just do more calculation, and you find that in general. So, this is a symbol that is used in physics. This is these are the Lorentz rotations, and this is the spinor representation of this. I'm just going to write it like this so I don't have to make something up on the spot. And given by this vector. So you have your rotation parameter vector, try to write bigger, dotted with the spinor vector, spinor matrix vector. You get the same thing here. So these are what the rotations map to. Then you have boosts for completion. These map to stuff that looks like this. We have a chi, which is kind of like a boost intensity vector, dotted with sigma. And then down here we have e to the minus chi, dotted with sigma. Two. So notice that these are inherently, so these are block matrices. So therefore, this representation is reducible. Okay, so that's calculation shows that this is true, but we can predict that this should be true because of our work on Clifford algebras. We already know that this is going to happen. Okay, why should this be true? This is because spin. Oh, I can delete this heading now. Give myself space. Right, so spin in particular lives in the even subalgebra, CL for the even subalgebra, which is isomorphic to the Clifford algebra of 1 degree lower, which in this case is actually 2 copies of 2 by 2 matrices. So this is one of these cases where you have a representation of the Clifford algebra, which was 4 by 4 complex matrices, and you're reducing it, pulling it back to a subalgebra that's a pair of 2 by 2 matrices, and your irreducible Clifford module splits when you restrict it to the even subalgebra. So this is why we actually get our 2 by 2 sub representations over spin by taking our CL4 representation. Right? So our CL4 splits over CL4. So we have psi is equal to U plus U minus, where these things are called Weyl spinors. So the 2 irreducible representations found inside of the Dirac representations, these are called the Weyl spinors. And they're somewhat more elementary than their sum put together. Okay. So, almost done talking about this topic. Almost out of time too. Take more chalk. That's it.
Of course. Feel free to use different colors as well.
Okay. I don't think I need different colors.
Okay.
All right. I'll just do these. Okay, here we go. So these are the Weyl spinors, and we're gonna let omega equal I or minus I, gamma 1, or gamma 0, gamma 1, gamma 2, gamma 3. So this is the volume element inside this Clifford algebra. And in the physics literature, they call this thing gamma 5 because of tradition, which is probably the worst reason to persist in calling it gamma 5, when all of this like edifice of Clifford algebra says that really this is the volume element. You're actually just splitting the Dirac representation using the volume element in the same way that we've been doing for this entire series of talks. They insist, no, it's really called gamma 5. Sure. You run the calculation using the Weyl basis, or the chiral basis, then you get this as your volume element. And so you can see that the Weyl spinors, so indeed U plus minus, the Weyl spinors really are in the eigenspace. Like I just said, this omega, this complex volume element, is splitting our Dirac representation into the plus minus eigenspaces. And the Weyl spinors are precisely those eigenspaces. So that's neat. Something that I didn't, nobody told me that. Okay, so that's basically what I wanted to get to with the Dirac equation picture, was just see why do we get this interesting splitting in terms of the Clifford algebras that we just spent with so much time figuring out. So there's maybe some further topics. One thing that you can do is called the Majorana basis. This is a very popular buzzword because these Majorana fermions, they're trying to use them in quantum computing. And I think they're succeeding, or at least the Microsoft chip is supposed to be a Majorana thing. Anyway, here's what it is. So this is just picking a different representation of the Clifford algebra so that it has somewhat different properties. And this particular representation has the effect that all of these matrices are actually imaginary. So, finish writing. So these are all imaginary. So this means that our Lorentz group representation Lie algebra thingies are all real. And so the Weyl spinors are called chiral spinors because sort of in certain interactions, if you just let them go do their thing, their spin will kind of precess. And the positive, the U plus are called left-handed spinors because they'll precess according to a left-hand rule. U minus are right-hand spinors. So the Weyl spinors, you tell them apart by their chirality, but the Majorana spinors you tell them apart by their charge conjugation. So this is the context charge conjugation. Is the thing. So I'm not going to say more about that because I don't understand it. But these two kind of bases, they're sort of like this. So you can have your Weyl spinors and you can have Majorana spinors, but you can't have like a decomposition of your state into Weyl spinors that are Majorana spinors. And they live in sort of different bases. Okay, so that's the Dirac stuff. That is the physics thing. I hope it was educational. Don't even have questions I'd like to ask about Dirac stuff. Okay, so now we're going to completely flip topics. Not really complete. No, we're not. So now we're going to think about, okay, this is all happening in some sort of trivial way. You have one vector space, you have one metric, and all of this is just happening one thing at a time. So what if we wanted to try to do this in a family? So spinor bundles. Okay, so what if the idea is, suppose you have some like possibly curved space-time, and then at every point you have your sort of a tangent space with an indefinite metric on it, your Minkowski metric on it, and sort of every point, it's like the physics are the same, but also there are some substantial differences based on where you are in space. And so the tangent bundle, the Clifford algebra that's like acting on your spinors at that point is actually going to vary from point to point. Things aren't exactly the same at every point. And so what we want to do is think about, so I'm going to write down the setup. We're going to sort of keep in mind when we try to do this in a parameterized version. So X is a nice space, some nice space. Where nice means whatever it needs to mean. It might be a manifold, you might need it to be an actual, smooth manifold. It could just be a CW complex at times. So we're going to take a bundle over X. And let's try to stick to this particular picture. So it's a four-dimensional real bundle with signature 3, 1, meaning that this inner product, which varies from fiber to fiber, in each fiber, it is an indefinite inner product with signature 3, 1. So it's like having a family of Minkowski spaces or like a Minkowski spacetime manifold. Except you can just take it as a bundle. It doesn't have to be the tandem bundle of something. And so we're going to assume, in particular, that B is orientable to begin with. So we can think about forward time, for example. So we're going to want to take this and build out of it a bundle of Clifford algebras. We want to build say A over X, so that the fiber at a point X is going to be just given by, maybe not even isomorphic, but equal to the Clifford algebra of the fiber Bx with the inner product that's defined over X. We want to build a bundle that's fiber-wise just the Clifford bundle of B. Okay, well, we can do that, and we can do a lot of other things with a really general construction that I like to call, well, I've started calling the action product. This is going to be like pure topology. So let X be a right G space, and let Y be a left G space, and then define the following thing, X cross Y over G. So first take the product, X cross Y, quotient by an interesting relation. So I'm trying to construct something here that acts like a tensor product of modules over an algebra, except it's two topological spaces that are being acted upon by a topological group G. So all you really can do is say, well, if we're acting on X by G, this should be, right, the property of the tensor product is that you can move the scalars through the tensor symbol. Now I'm just declaring that you can move the scalars past the comma. So this is like a tensor product for group action. And it's kind of weird to think about it until you work with it for a little while. And it's still pretty weird to think about. So I'm going to give you the properties that are important to us for doing these constructions. Wrote this down somewhere crazy. Okay, here it is. So properties for this thing. You can't project to X or Y in a well-defined way, but you can project to their quotients by G. So we have X mod G, and we have Y mod G on the left. That's Y. And in particular, you take pi X inverse of any orbit here. This is actually equal to Y. So let's call this X naught. This is Y modulo the stabilizer of X naught. So all elements of G that fix this particular X naught. Similarly on the other side. So the G orbit of the point Y naught, in this case Y, fiber over this projection map is going to be this. So this is kind of like a step. Remember over every point and what are the stabilizer subgroups, except you're mixing two actions together. So here's some consequences. If the action of G on Y is transitive, every action decomposes into a union of transitive actions. Then the result is that X, where are we? Yeah, X cross, sure. X cross over G mod H, X mod H, where H is the stabilizer of any element of Y, because it's a transitive action, they're all the same. So this is something that's true for homogeneous spaces. If you take G modulo some subgroup, and you take this action product, what you're actually getting is X mod whatever that subgroup was. This is going to be relevant later. And then if the action of G on X is free, so then the stabilizer subgroups are all trivial. I.e., if X, in fact, is a principal G bundle, then taking X cross over G with anything here, the projection to, what is it? This, so X mod G is being the base space. This is a bundle with fiber. What's the other thing? Y. Yeah. So this is one of the effects that this action product has, is if one of these is actually a principal bundle, a principal G bundle, then by choosing the action of G on anything Y, this product has the effect of replacing the G fibers with Y in a way that depends on what is the action of G on Y. So this implements our fiber replacement procedure, which we used to just do by saying, okay, well, you take this local trivialization, you have all of these transition functions, they come from a group representation. You can have that group acting on any fiber, and glue them all back together. But this formula just does it for us automatically. So we use this as a convenient notation and a convenient computational tool when we're just constantly plugging in different fibers and taking associated bundles and things like that. So we're going to use this to make our bundle of Clifford algebras, and we're going to use this to make bundles of modules that are representations over Clifford algebras, et cetera, et cetera. So we're going to say, so the G has underlying, then says how O31 bundle. We're going to call that EP. So that Clifford algebra of B is be equal to the underlying O31 bundle cross over O31 with the Clifford algebra of the degree 3-1, where the action of O31 of the Clifford algebra is the usual thing. That's by algebra automorphisms via the universal property. So remember, this thing acts in a metric preserving way on the vector space. Anything that does that induces an algebra automorphism of the Clifford algebra property. So that's the representation that we're using to plug the Clifford algebra in to replace the V fibers with this Clifford algebra. So this is now actually a bundle of algebras. Each fiber actually has an algebra structure. These algebra structures vary from fiber to fiber. And so sections, in particular sections, gamma, CLV, is an algebra. So this is the thing, this is our bundle of Clifford algebras that we want to do physics at each point. Yeah. All right. So in the unparameterized picture, we sought out irreducible representations of the Clifford algebra, right? And so we can ask, can we find a bundle? So M over our base space X, so that, and a action, say, Clifford algebra of B tensor with M. So this is the tensor product of two bundles over X. And so we want to define a module structure on this M as a module over this bundle of Clifford algebras by just declaring that, okay, over each point, there should be a modular action, and these modular actions vary continuous. So can we find a bundle and an action? So we would call this what? Bundle of Clifford modules, or I think this is actually the Spinor one. Anyway, can we find such a bundle where Mx is an irreducible CLBX logic? So this is an interesting question. So it could be the case that M does decompose into two bundles at each point. But it's possible that the decomposition can't be made consistently. So it's possible if you make the decomposition over one point, and then you sort of follow around the topology and get back, then the two decomposed subspaces might end up being identified after you do this twist. So that's like similar to the way that you tried to define an orientation by finding a section of the alternating line bundle. There might be sort of topological twisting obstructions for your bundle M that make it so that even though each fiber it decomposes into irreducibles, these irreducible modules somehow like glue themselves together at the global level. And there's no global bundle decomposition of the irreducibles. So the answer is not necessarily. So what we're going to do in order to enforce it, so we can enforce with something called a spin structure. So like I said, this is kind of like an orientability condition, but at a bit of a higher level, especially since we're already starting with orientable bundle. So it's going to turn out that, so if our bundle B, so what we'd like to do, right, what we'd really like to do is we have a module. If we took a module over the Clifford algebra, just some any old module, we'd like to try to plug it in to the principal V bundle in order to get a bundle of modules and a natural action of this on that. But the problem is that, So this bundle of modules is inherently a spin representation. We're trying to plug in the spin representation using the orthogonal group. That isn't always going to work. So the idea of the spin structure is that if instead of this being a principal O bundle, we could actually construct this bundle out of a principal spin bundle. So if the structure group of the bundle is actually spin, then when we plug in the spin module, since the spin is actually acting on this thing and preserving these invariant subspaces of the Clifford algebra module, when you go around the base space, you're going to keep this constant and consistent separation between these two submodules. Okay, so that's intuitively what is happening, what is about to happen. So now we'll just write down some math and some symbols, and you can sort of digest it later. Okay, So let's say definition. So let P be a principal SO bundle. So I'm really being abusive with my notation here. I'm just deciding I don't want to write 3-1 all the time, but also everything I'm about to say applies to every possible signature. So instead of just writing PQ all the time, I'm just going to write SO. Because a lot of these things also sort of carry over to the stable world, but just when I write SO, just imagine that there's some fixed signature that we're always keeping constant, and we're looking at the special orthogonal group of that signature. Possibly the orthochronous ones. Right, yeah. Yeah. Okay, so let's suppose we have a principal bundle over SO. So a spin structure is a, like I said, what if it was a principal spin bundle? But it can't just be any principal spin bundle. It has to relate to our original spin bundle in a way that's consistent with the usual double cover of SO by spin. So we're going to enforce that by saying that we get an equivariant double cover. What do I mean? So you have your spin bundle P. Let's call this, forgot I had to call it something, P tilde. So let's take our principal spin bundle P tilde. So part of that structure means we have an action by spin. And we have a double cover going to P. And to be an equivariant double cover, I just mean that if we take our principal SO bundle downstairs, or principal spin bundle upstairs, and if this is the product of the projection, so spin to SO, the double cover is the adjoint times whatever our double cover of our principal bundles are. So what this is saying is that this double cover, the principal spin bundle over the principal SO bundle, fiber-wise, it just looks exactly like the double cover from spin to SO. This is codified by considering the global action of spin and SO on the two bundles, which act fiber-wise. So this is a spin structure. And so using this spin principal bundle, now we can just plug in any old module over the Clifford algebra. You'll want to do that already? I think so. Yeah. So then what we can do is this. So if V is a, let's say SOPQ bundle, I guess. So with structured group SOPQ, with spin structure, let's say P tilde again. And yeah, let's say this is the principal SON bundle. So if we have such a thing, then we get Clifford algebra. Yeah. So if we have this, and suppose M is a module over the Clifford algebra, the signature, then we get the Clifford algebra. What am I trying to say? So we already defined this. This is P B cross over SO with R P plus Q. No. Clifford PQ. But it turns out that this is also the same as the principal spin bundle cross over spin. No, it isn't. Yeah, it is through the adjoint action. So where spin is acting through SO in this case. It's not acting as a subalgebra to plug this in, it's acting through SO. So this is a little slight difference. And then we define SM, the module of this, we define this to be, take the spin bundle, use the spin group, the spin module action to plug in this bundle M. Now, once we've done that, we do get a genuine Clifford algebra action on this Clifford bundle M. So this is a Lawson-Michelson proposition. And it was, what have we done, 3.8. This is part 2, actually. So this says that SM is a, what's the right word to use here? Clifford bundle module in the sense that we get an action ELV censored with SM to SM, which fiber-wise is Clifford multiplication. And so not only is it a module, but if M splits into M plus and M minus, then if you take the spin bundle, so P spin, M plus plus M minus, this just actually does split up as a direct sum. So the associated bundle where you plug in N plus the associated bundle where you plug in N minus. And again, you can see this kind of from a transition function perspective, because these are modules over spin, irreducible modules over spin sub-representation. And so, right, if you're keeping these invariant over each transition function, then globally you're going to be able to keep them apart. So these things behave the way that we want them to. This is our clear theory of spinor bundles. Yeah, so such a thing is going to be called the spinor bundle. So over a space-time manifold, if you have a spin structure on your space-time manifold, then this is the way that you construct representations for your local Clifford algebra. And okay, yeah, I have to make this clear. So if you have a spin structure, you can do this, but this isn't an only if. This is not an only if. There are other ways that you can ensure that all of your modules split as direct sums of irreducible ones. The spin structure is just kind of the most easy to work with, kind of easy to conceptualize. So unless they're all out of order now, I've said what is good so far. Let me try to find the last little bit that I want to talk about. We had Venus maybe, not today. So okay, yeah. So now this is great. So we've identified this condition that you can put on a bundle V to ensure that you have a really good theory of spinor bundles. Decompositions are preserved after going to families. So the next step, so if we know we have this nice criteria that we can check, now the next step is, well, how do we ensure that a bundle actually has a spin structure? If the bundle does have a spin structure, how do we count how many spin structures? Okay. So I'll end with this last discussion, try to make it quick. Neat. So we'll probably spend too much time. So we have two. So which bundles admit spin structures. And if so, how many? Okay, so here's an example of a spin structure. So if we have E spin, which I'll put an N here again. E spin, the classifying space for principal spin N bundles. We have a canonical map, which is B of the adjoint map, the SON, classifying space for oriented n-plane bundles. So if you take the universal SON bundle and pull it back, bad star, crazy notation, I apologize for this, but this is, it is. So this thing is a principal SON bundle, and we have E spin, double covers, this pulled back principal SON bundle. So in fact, this here is the universal spin structure. And in fact, if you go and do it, you'll find that AN oriented bundle B admits spin structure if and only if its classifying map lifts. Oh, it's not too crappy down here. So you have your space X. You have your map to be SON, witnessing the fact that it's an orientable vector bundle of rank N. We have our map from B spin to Bn, given by the adjoint, and a spin structure is just given by the pullback of the universal spin bundle, and it double covers the pullback of the universal SON bundle. So a spin structure admits a lift if and only if its classifying map, orientable bundle admits a lift, spin structure if and only if it admits a lift to B spin path. So this is a homotopy theory characterization of when does a bundle admit a spin structure. And I think we discussed maybe a million years ago, maybe last term, how to solve lifting problems. So yeah, just in the sake of time, I'll just skip the motivating example and jump right into this one. So recall we had this defining, not really defining sequence, but we do have this long exact sequence. And I'll just skip out on indefiniteness now because I'm used to doing definite stuff. So we had this short exact sequence of groups. Z mod 2 is a normal subgroup of this. And then we can de-loop. You can continue this sequence to continue a vibration sequence going to BZ2, B spin, BSON, B squared Z mod 2, because this is the abelian group, you can just keep taking B forever. But this isn't an abelian group, so you can't take B squared. This is where your sequence ends. And this is a vibration sequence in the sense that every sequence of three things is up to homotopy equivalence of vibration. So this thing, this part of the sequence, if we convert this into a vibration, then a map into BSON lifts to B spin means that we're actually just taking a map into here and homotopying it into a fiber. By the homotopy lifting property, what we can do is project it to the base space, take a null homotopy of that, and then lift that null homotopy to get us a map into the fiber. And vice versa. The homotopy into the fiber is a null homotopy into the base space. So therefore, we have an equivalent up to homotopy characterization. So B to B That's O. B is a map from X to B as O n lifts if and only if the composition in this map is null homotopy. Okay. So I'm not to take my word for it that this is not a null homotopic map to begin with. So this actually represents the second Stiepel-Whitney class, right? So B squared of Z mod 2, this is A Z mod 2, 2, Eilenberg-MacLane space. So this represents degree 2 cohomology with Z mod 2 coefficients. And yeah, this map represents the universal second Stiepel-Whitney class. So what this is saying is B admits the spin structure if and only if the second Stiepel-Whitney class of V vanishes. Remember, we're assuming that V is already orientable. So it doesn't really make sense to talk about a spin structure if you don't already have that principal SON bundle. So at this point, W1 and W2 would be both vanish in order to make a bundle whose structure group is spin. So how many spin structures? Okay, so B spin BSO. This is a BZ2 principal element. Turns out that not only is it a bundle with fiber Z mod 2, but Z mod 2, at least at the homotopy, has a free action on B spin N. And so, in fact, B Z mod 2 acts on the space of lifts given a function of X into here. If you're given a lift into the, right, if you have a function into the base space, you have a lift into a principal bundle, then the G action on the principal bundle is acting on the space of lift to give you another lift. In fact, up to homotopy, in the appropriate sense, since I don't have time to spell out, this action is free and it's transitive. So it's called a torsor. Choose a spin structure, then maps into BZ2, give you a bijection between the set of all spin structures. Yeah, then you get a bijection between maps into BZ2 all spin structures. So it goes. But right, maps into BZ2. Right, so this is also, this was a KZ2, this is a KZ2, this is the first cohomology of X with Z2 coefficient. So this actual abelian group, this parameterizes spin structures when a spin structure exists. So either there are no spin structures, but the set of spin structures is in bijection with this first cohomology group. So that's spin structures. And so you can go and repeat specific examples just based on cohomology. Sometimes, all of the cohomology groups that are relevant all vanish, right? So the spheres in degree 3 and higher, those all have, every bundle over them is spin and has a unique spin structure. But over the two sphere, you can have bundles that aren't spin. These are the ones whose Euler classes are bond. Yeah, I'm not going to go into a huge amount of talk about that. Right, so here's spin structures. So I'm going to talk about so I'll close with the ladder of the structure. So a map into BON, this is just giving you a plain old vector bundle. right here. So any rank and vector bundle, you have a principal underlying ON bundle classified by map to BON. So then we have a map to BZ2 called the first Stiefel-Whitney class. So that the homotopy fiber of the first Stiefel-Whitney class is actually BSON. So that was a really fancy way of saying that our BSON is actually as a fibration over BON is classified by this map to BZ2s, right? This is a this is a double cover because it's classified by map into the classifying space of double cover. And so a vector bundle is orientable if and only if its first Stiefel-Whitney class vanishes. And such a lift is called an orientation. So the next one up that we just discussed, we can start writing Heisenberg McLean spaces instead. We saw that the W2 goes to 0 here, if and only if you get a lift to be spin. The next one up in the tower is B spin. And the lift, again, this is a spin structure. So it turns out, as we're making these lifts, so this thing has a non-zero fundamental group, but when we kill W1 to make BSON, we also kill the fundamental group. Turns out this is actually the one connected cover of BON. Probably have the indices on this thing wrong, they always get it wrong. But this space is simply connected, and this projection map uses isomorphisms on all homotopy groups higher than 1. When you have W2, so you're essentially killing W2 to get to spin N. But you actually end up accidentally killing more. So the first non-zero homotopy group of this thing is in degree 4, in fact. This is actually BON, I think the 3 connected cover. So I'm using this as the notation, possibly this isn't the correct notation. All of the homotopy groups up to and including degree 3 have been killed, and all of the higher ones have been left alone. So it turns out that the next element of homotopy is described in degree 4 by something called half of the first Pontryagin class. So this goes to 1 over 2 E1, and this lands us in a KZ4. And when we take the thing that's killed by, when we kill the 4th homotopy group by killing half of the first Pontryagin class, the thing that you get started out as just a classifying space, but later on we actually found a group called string N. The next thing up the tower is called string N. This is BO7. So the first non-zero homotopy group there is in degree 8. And so I think I've done these. I think I've done these brackets in the wrong degrees. Maybe up by 1. Anyway, that's fine. So then you can get a string structure. I'm trying to indicate where all this is going. In the modern world, all of this spin business turns out that if you're, put some additional conditions on your bundle to give it a string structure, all of this stuff about Clifford modules and K theory actually gets replaced by some more complicated algebra and cohomology theory called TMF, topological modular forms. So I don't think it's a good idea to start talking about that now, but there's an idea of orientation where the actual orientation gives you something in different cohomology here. So this orientation for a closed manifold, having an oriented fiber, so for a closed manifold, having an oriented tangent bundle means you have a special class in your ordinary cohomology representing the orientation, and it induces things like Poincare duality and Thom isomorphisms and things like this. When you go up to a spin structure, instead of finding your orientation as an ordinary cohomology, it's actually in real K theory, KO theory. There's something, a general construction, parametrized version of the Atiyah-Bott-Shapiro construction that we did last time, constructs for you orientations for spin men. which result in the A hat genus, which is a ring homomorphism going from spin boardism, which gets the omega spin star. Yeah, remember it should be up or down. Goes to KO star 4 point. And then, so string structure gets a lot more complicated. But what we get is something called sigma. This is Witten's sigma genus. And so this takes string manifolds up to string cobordism and spits out values in the cohomology theory given by topological modular forms. So this whole business about Dirac and spinors and spin structures has evolved today to be one step higher, talking about strings, which is much, much harder. And this tower does keep going into D5 brain, which I don't know anything about. D10 brain, dot, dot, dot. So there's presumably an entire family of cohomology theories, which are the appropriate receptacles for orientations corresponding to all of these different kinds of higher structures. That's one area that's happening right now, really, really big for the last while in theoretical physics, is studying these higher structures. Yeah, so I will stop. Thank you for listening. Any questions?
I suppose this kind of classifying space stuff, that's not Michelson, right? That's kind of more modern than Michelson.
Well, that's like classic.
Okay.
So this is going back to like Steenrod in the 1930s with people like that. So the idea of classifying bundles or cohomology theory or all kinds of things like that, like constructing classifying spaces. Yeah, that was like 40s and 50s.
Okay.
Yeah.
And then, so when we're kind of determining if we have these spin structures for these bundles, we're not presupposing any metric or anything. It's just totally like.
That's right. Yeah. So once we started here, right here, like we didn't have anything to do with metrics anymore.
Yeah.
Like I could have done all of this with an indefinite signature. And I think things are kind of topologically different, but I think, yeah, I didn't want to, yeah, I fixed this because this is something that I know for sure. But I wasn't actually sure like what is the cohomology of PSO-PQ. Right. I don't actually know off the top of my head what is that. So I didn't want to just say that there is a second Stiefel-Witten class here that obstructs it. It possibly is like exactly the same picture, but I actually haven't thought a lot about what actually is the classifying space of BOPP. Might be the same.
I guess I just think it's physically interesting that like some sense you have like your spinners on your space time before you have like metrics necessarily like.
Yeah. Well, we did talk about all of that Dirac stuff in terms. Yeah. So talking about the Dirac equation itself, doing all of that particularly involved the metric because you had to start with relativistic stuff.
Yeah, like you do fractions and stuff.
Yeah.
Yeah.
But yeah, this is kind of a version of spin that is. I mean, I guess you could call this non-relativistic. This is like non-relativistic spin actually.
Yeah.
Because it's actually just a non-Minkowski metric. Yeah, but yeah, exactly. So this notion of spin isn't really inherently relativity. It's not really inherently quantum. It's more just like, well, okay, you've got some indefinite inner product on a vector space. This leads to a Clifford algebra, and this contains a really nice subgroup. It's called spin. This manifests itself in relativity and quantum mechanics. I take the perspective that it's like purely algebra. Physicists discovered it in the wild on their own. It's really cool that this pure algebra just manifests itself in the real world.
So it's like purely the just indefiniteness of the inner product that gives rise to spin.
No, not even,
No.
because these are definite inner products.
Oh, okay.
It's really just like the non-trivial double cover of SO.
Oh, that's it. Yeah.
Yeah. So like, yeah, the identity component of SO, as long as like at least one of P or Q is bigger than one, then like the identity component has a fundamental group of Z mod 2. something like that. Like in the degenerate cases, it's not Z-mod 2, but whenever the fundamental group is Z-mod 2, the connected component of the identity has a non-trivial double cover, which is unique up to isomorphism. And that's the thing that's called spin. It's the spin.
Yeah, nice.
So this whole construction of like realizing the spin group inside of a Clifford algebra, you didn't actually have to do that. We could have used pure covering space theory to just deduce that there exists a group structure on the double cover, such that blah blah. But putting inside of the Clifford algebra meant that the representation theory of Clifford algebra just like immediately accessible to us. So that's why it's better from this perspective to think of it as living inside of the Clifford algebra.
And then, excuse my ignorance, I haven't done much algebraic topology, but how should I think about these classifying spaces? DOSO, SON.
You should be thinking of them as like a moduli space, like a universal space of SON torsors.
Okay.
So that your map from X into the space at every point, it chooses like a torsor. Like it chooses something that has a free intransitive action by SON. And then yeah, these actions vary continuously. That's exactly what a principal bundle is. It's just a bundle of things who are homeomorphic to SON. And you have this global free action of SON.
So there's some universal property?
Yeah, kind of like the thing that defines, characterizes the classifying space, kind of the homotopy is just because of the fact that it classifies things. So, right, so for all principal, or rather, yeah, so it's a representing object for the functor principal G bundles. So prin G space is, so this is isomorphism classes of principal G bundles. This is a natural correspondence with homotopy classes of maps from their variable to BG. And the idea is that there's a bundle EG over DG of the universal bundle so that any other principal bundle is pulled back, right? So principal bundle here corresponds to a continuous function here by just pulling back this EG. So this is, I guess, in a sense, the universal property that classifying spaces have, but it's just the definition that they represent a functor.
Okay, I see.
Yeah, and so because they're a representing object of a functor, it turned out to be unique out of homotopy equivalence.
So what's that square bracket? That's you said homotopy?
Yeah, these are homotopy
Okay.
classes.
Oh, homotopy classes. Okay, okay.
Yeah, so when we actually construct these usually as a space of all n-dimensional planes in R. So this is usually how you just construct like a Grassmannian of all n-dimensional planes in R infinity. And then that turns out to be the same, or at least a model of BSON. Because in that case, you can think of it as like, well, for each point of X, you're literally just taking a plane. And yeah, because you have planes with orientation, you have a continuous choice of orientation as you go through the planes. So there are models of the classifying spaces that are actually like vector spaces with structure, but that's sort of like a special case of these groups that naturally act on vector spaces. Just have an arbitrary group G that lives out in the wild, like some abstract things, and BG makes the most sense to think of as like universal moduli space of G actions.
Okay.
Free G actions. Yeah. Yeah. Oh, and there's, I don't know, maybe, yeah, you just did, but one way that you can always ensure that you get a classifying space is that BG is always the quotient of a intractable space. So, yeah, so this is like a characterization of the universal bundle. If you have some principal G bundle out in the wild, you already know it's a principal G bundle. If that total space is contractible, it's actually automatic that the base space is a classified space. So up to this like pullback isomorphism, there's actually only one contractible principal G bundle. That's the really surprising thing that makes the whole classifying spaces picture kind of work out. And this contractibility G leads to a lot of things. Good question.
I guess now it's time to learn about the brains, the BF brains.
Yeah. String's too easy. You have to go to fiber.
Yeah.
Yeah, I don't know why they call it that exactly. Certainly because of world brains and stuff from string theory. And think like in physics perspective, they probably just treat it as like more characteristic class advantage. Like the second Bontrier eigenclass is 0 now. Dot. Um, but yeah, from a topological perspective, it's just a connective cover of the classifying space of the I don't know what the TMF. Super hard. I was saying before you got here, it's like you actually need to know elliptic curves and modular forms. It's not just for show.
This stuff is like 80s, 90s, 2000s.
Everything that I'm talking
I
about.
mean, like the string stuff, like the Witten genus.
Yeah, Witten genus was like 1986 or something. Yeah, so all of the big string stuff, Witten genus, yeah, like 80s and now so
It was pretty modern.
relatively modern. All this Clifford stuff, I think it's like Atia. Think all of this Clifford module stuff, like most of this was just, this is all in the Atia Shapiro paper. So I'm not sure if Atia came up with these ideas for the purpose of describing K-theory in terms of Clifford modules, or if other people were already thinking about it separately. But he took it as far as it would go. Well, actually, probably not. This leads to index theory. This is the framework that you can actually phrase index theory using this stuff about Clifford modules and Clifford algebra bundles.
Very nice. Very nice.
Thanks. Thanks.
So we can stop the recording.
So I could have written down the Dirac operator. So